Okay, hello everybody. Our today's speaker is Michal Opler, and he will talk about multi-agent path finding. For his year.
Okay, thank you for the introduction. So this is joint work with Fivos, Dusan, Matthias, Nikos, and Tunk, distributed across this department and Computer Science Institute at Charles University. I'd like to thank Fivos for providing these slides that I slightly adapted and extended. And yeah, let's get into it. So multi-agent pathfinding in our world is a graph problem, essentially, where you're given a graph with some initial configurations of agents on vertices. And the task is that each agent has some prescribed target. So I hope the colors can be at least somewhat discerned. This blue robot wants to go to this blue vertex. This red robot wants to go to this red vertex, and this brown robot wants to go to this brown vertex. And now we're looking to compute a schedule for them, where in a schedule, in each round, every robot can move to an adjacent vertex. It doesn't have to, it can stay where it is currently. And additionally, no two agents can be on the same vertex during the same round. And we also require that two agents cannot swap along an edge, so they cannot perform this sort of crossing over a single edge. This is sometimes not part of the definition, but we feel that this is the more natural variant where you also forbid the robots to swap places. And the question is, what is the make span, meaning the minimum number of rounds in a schedule that routes every robot to its target destination? So here we have a simple tree. We're gonna need at least 5 rounds because that's the distance of the blue robot from its target. But in fact, we'll here need 6 rounds. So in the first round, now the brown robot is trying to get out of the way for the blue one so that the blue can pass. And now the red also starts moving, and but now the red wants to go through, so the brown has to move to a side to let the red ones through, and finally they all just reach their destination in 6 rounds. So easy, right? It's such a nice problem. For sure that has to be somehow easily solvable. Well, not really, right? So this problem has been shown in this graph variant to be NP-complete by Sulinek in 2010. And since several strengthenings are available, so you proved that it remains NP-complete on planar graphs. And so people on one side of the community focused a lot on heuristics, right? On something like A-star, some set-based heuristics, and etc. And we supported this recently, and other authors supported it by showing that it's even much harder. It's not just planar graphs, but it's planar graphs, even if we are asking whether the make span is just 2, whether we can route the robots in 2 steps. I like to point out that in 1 step, it's very easy because you don't have any choice. You just see whether there is any collision happening, and if not, then it's doable. So even for make span 2 and max degree 5, it's hard, and it's hard on trees, even on trees with bounded degree, which we shown last year. And quite an interesting result from 2003 by Iban et al. Is that it's also hard on infinite grid with constant make span. So there are no obstacles. It's the full integer infinite grid, and you're essentially just given an starting and end position of each agent, and you're asking whether you can route all of them without collision in 26 steps. And this is also NP hard. So, what can we do in such a situation? Let me first also comment that there are some other variants that are possible. So you can replace that rule of parallel rounds with different types of movements. So you could assume that you only move 1 robot per round. You can also have like dense, require that the instances are dense in the sense that there is 1 robot on each vertex, and you're now, obviously you have to allow swapping, but now you're asking like what is the shortest schedule to get to from one configuration to the other, which is called token swapping. It can also remind you of some of these reconfiguration problems when you're trying to take one independent set to the other independent set. And so there are various different variants of this. You can require connectivity of the agents throughout the schedule, and etc. So, but like I said, the problem is very hard. So in here, in this community, people are interested about parameters. So, and what the previous results say is that, with respect to most structural parameters alone, the problem was already shown to be hard. So our kind of search was, well, can we do at least something, right? So, so we focused on the most restrictive parameters that there are, or that still make sense and are there, which on here you can see on the top. You can disagree with that, but here they're on the top. And in particular, usually in these parameter hierarchies, there are three usual suspects that go on the very top, which is the distance to clique, vertex cover, and max leaf number, where distance to clique and vertex cover are kind of complements of each other. So distance to clique is size of the smallest set, such that when we remove it, the graph induced on the rest is a clique, it's a complete graph. And vertex cover is the size of the smallest set, such that when we remove it, the rest of the graph is edgeless. So the rest of the graph induces an independent set. So those two I assume you probably heard about. And then the third very restrictive one is called max leaf number. Its definition is that it's the maximum number of leaves in a spanning tree, overall spanning trees of that graph. But somehow more naturally, it can be imagined that the graph has a small max leaf number if and only if it is a subdivision of a constantly small graph. So if it's, if it has max leaf k, then it's a subdivision of a graph of size linear in k and vice versa. So really, in graph with small max leaf number, most of the vertices are degree 2 vertices that lie on long paths between, and there are only few interesting vertices that have different degree than 2. Okay, so these are, like I said, the most restrictive ones on this particular figure. So can we use them algorithmically for solving the multi-agent path finding? Well, 2 of them we cannot, and even in a more strongly sense that the problem remains hard on graphs of small vertex cover and small max leaf number, but moreover, even if those graphs are trees. So we can show that they're NP complete even on trees that have just 9 internal vertices, so almost everything is leaf, and vertex cover 7, and also on trees with 11 leaves, which means the tree is almost like 11 paths joining somewhere somehow. So even in these extreme cases, the problem still remains NP complete. And the only redeeming case is by the distance to clique, is that when the distance to clique is small in the graph, then this problem can actually be solved by an FPT algorithm, meaning by an algorithm with running time, some function of the distance to clique times polynomial in the size of the graph. Right. Before we move on, any questions to this? Okay. Right. So in the rest of the talk, I will cover somehow try to sketch the FPT algorithm, and then I'll also do the same for the reduction for the trees with 11 leaves. I'll skip the reduction for small vertex cover. It's mostly due to time, both time needed for presenting and time needed for me to drawing all the figures. But it's a really nice reduction, and if you're interested, please come ask me afterwards. I'll be happy to give you the main idea of that. But as we start with the positive result, meaning the FPT algorithm, distance to clique. Okay. So just sort of to give you some graph with small distance to clique. In this particular graph, there are 5 these gray vertices. When we remove them, we're left with graphs with a clique. So we say that this has a distance to clique 5, and we will denote here the distance to clique by k. And we will refer to these gray vertices as the modulator to clique, and we'll also be denoting it by capital M at some point. All right. So what is the sort of general idea behind this algorithm? Well, if we get some instance where the graph has a small distance to clique, then first we show that if the instance is solvable, if there is some schedule, then there is one that has makespan bounded in the distance to clique. So bounded by some function. So meaning like if there is a schedule, there is a short one that is independent of the size of the graph and depends only on the size of the modulated to clique. And then we use this to construct a new instance of Multiagent Path Finding, which is of a size bounded in the distance to clique. It's not necessarily equivalent to the original instance, but it's equivalent if we find this with respect to solutions with certain additional properties. So we show that the original instance on input has schedule of certain makespan L, if and only if this reduced instance has schedule of makespan L such that something additional holds for it, which we will be able to check. And then once we show this, then the algorithm given this reduced instance is that we just compute the optimal schedule for the reduced instance where we guarantee this additional property. But since this reduced instance is of size bounded in K, then we can use whatever brute force algorithm we can do better, but if we wanted to, we could just use any sort of brute force algorithm that, for instance, we could enumerate all possible schedules of that length and then just find the shortest one, which has this additional property. Okay. Any questions? Sure. Okay. So I'll mostly focus here, in fact, on the first one, because it's surprisingly tricky to already show that there is a schedule with short makespan, which is, it shouldn't be surprising intuitively. Like you have this large, like majority of the graph is one large clique where you can do whatever you want almost, and then you have only this small modulator. So somehow, you would think that of course you can rearrange the agents on the clique within small number of steps and get to a desired solution. But the thing is that the swaps, the fact that we forbid swaps from happening is the hard part. Okay. So how do we do that? Well, a key, I wanted to write observation, but it takes a little bit of time of proving, is that if we have any instance of this multi-agent path finding on a clique, just on a clique, no modulator, and the clique has at least 4 vertices, then there exists a schedule, non-colliding schedule with makespan 2. If we have not forbidden the swaps, then there is always schedule of makespan 1. Just route everybody to their destination, but that can introduce swaps and kind of showing that in all possible things that can happen, you can always kind of deal with it within 2 swaps. Kind of depends on some structure of the permutation that is there and whatnot. So, but you have to trust me on this one. Okay, so within 2 steps, you can rearrange the agents on clique from any configuration to any other. So we distinguish 2 types of agents. The agents A1 will be denoted red. So those are the ones that start or end in the modulated to clique. So they start or end in these 5 vertices that are not part of the clique. And observe that the set of agents A1 is small. That can be at most 5 agents that start there and at most 5 agents that ends there. And A2 is the rest of them. Those are the blue ones. And the idea is that, if we don't care about the optimality of the schedule, just showing that there is a short one, we can essentially treat the agents, the blue agents, as anonymous agents, and just kind of move them around as much as we want. And then at the very end, when we rearrange the red agents to their final destinations, we can then use the key lemma to rearrange the blue agents within 2 steps. So as long as we're not interested in the optimal solution, just showing that there is a short one, then we can first compute a solution where we treat these blue agents as anonymous. And at the very end, we rearrange them in 2 steps because we can do so on any 2 configurations on clique. Okay, does this make sense? All right, so now we're in this situation where we consider these blue agents as being anonymous and not distinguishable. And we define, we call a snapshot type of a configuration. And the snapshot type captures which of the red agents are within the modulator and where they are. So you would remember that this red agent is here, this red agent is here, this red agent is here. And for the blue agents, we will just remember which of the vertices in M are occupied by some blue. So in other words, for each vertex of the modulator, we have either one of the agents of A1 stationed there, or we have some agents of A2, or there is nothing there. Which means that for one vertex of the modulator, we have size of A1 plus too many options. Either there is one of A1, or there is none, or there is one of the blue agents. Okay, so the number of different snapshot types is bounded by the distance to clique. Because like I said, the number of agents that start and end in clique is also bounded. It's at most 2K. So now we want to somehow show that we can find a schedule where some specific where any snapshot does not appear more like a lot of times. That's not the shortest one. In fact, we can show that every snapshot type appears at most thrice, 3 times in an optimal solution to this problem. So imagine that this snapshot, the first one, is the same as the last one. So these 3 red agents are exactly the same. And imagine that in between them, there is more than one step. So there are at least 2 rounds in between. We claim that we can forget all of these intermediate steps, and instead we put in single intermediate step, which has the same configuration on the modulator to clique, and on the rest of the graph, well, we use this lemma that on clique we can rearrange things within 2 steps. So on the rest of the graph, on the clique, we have some initial state here and some final configuration here, and then we just use the lemma to do this transformation within 2 steps. So in this way, whenever a type appears more than 3 times, then its first occurrence and last occurrence is more than 1 step away, more than 2 steps away from each other, and we can shorten it by doing this. So in this way, each snapshot appears at most 3 times, and we get that we can, in fact, find a schedule for this variant where the agents in A2 are anonymous, that is on bounded makespan, and then we can add 2 extra steps for reconfiguring, like making them non-anonymous again, kind of reaching their destinations. So that means that if there is a solution, there is a solution of small makespan. Is that clear? And when we have this, let me just sketch how we get the reduced instance, because it's a bit more complex, but the idea should be not that hard. So we know that there's a solution of short makespan. So as usual, when we look at the clique, the modulator induces some bounded amount of types within the clique, given the neighborhood of the vertices. So, depending on what is the neighborhood of a vertex in the clique, we can partition them into 2 to the k types. And similarly, we can partition these blue agents in A2 into 2 to the 2k types, simply basing on types of their start and end vertex. So, I look in which back the agent starts and which back the agent ends, and I have 2k times 2 to the k times 2 to the k types. And now we describe how to find a set of agents that are still bounded size, such that each of these backs is either too large, it's like larger than 3 times the number of these agents, or these sets of agents already contain all the agents that start and end in that type. And once we find this, we essentially define the reduced instance by keeping only the agents from this set and the nice and well-behaved agents of A1. And we just cut down each of these backs q tau just to size 3 times the number of agents. So in this way, we make it into a graph which is a bounded size within k. And now the hard part is showing that the original instance has a schedule of make span L if and only if this reduced instance has also a schedule of make span L such that, moreover, it always contains at least this many agents in the modulator at all times. And the idea why we want this is because this is a necessary condition, because in this reduced instance we're forgetting some agents, and we have to make sure that when we reconstruct the solution for the full instance, that all the forgotten agents fit within the clique. And we will be distributing the other agents only within the clique. And so it cannot happen then in this reduced instance where, if the number of agents is larger than the size of the clique, it cannot happen that we leave empty space in the modulator, because then when we would return the forgotten agents back, we would not have place to put them, because the modulator would be empty and we would need some place extra. So this is a necessary condition, but it's also sufficient, and that's not at all easy to see. There is sort of an argument that when you have a solution for the reduced instance, you use some sort of matching whole theorem kind of arguments that essentially give you the positions of the remaining agents throughout. And they work because essentially everything that you forgot was large enough to kind of have some sort of freedom of rerouting these things without introducing swaps. And like I said, it's not obvious and not easy at all. And so when we have this, then the algorithm just finds the optimal schedule for this reduced instance, which guarantees this additional condition that the modulator has to contain at least some number of agents through every step. And that's the sketch of the whole algorithm. So, and like I said, most of these issues actually arise from the fact that we're forbidding the swaps, that essentially all this machinery has to happen because we're forgetting certain agents, and then when we're putting them back, assigning them to vertices, we cannot make them cross each other. And we have to somehow prove that even though we're not tracking them explicitly, there is always a way to do that. Okay, so in that case, let me get to the hardness proof for the max leaf number. And this one is, at least the basic idea is very understandable, and it's a reduction from a very neat problem, which is pancake flipping. You heard about pancake flipping? So here it's written in permutations, but the motivation is, you have a stack of pancakes, each one of different radius, and you want to sort them like a Hanoi tower from the largest one to the smallest one. But the only operation you have available is that you stick your spatula, that's the word for that tool, somewhere in the middle, and you flip the top. And you're asking essentially how many of these flips you have to do in order to get it to the sorted order. And then if you want to, if you were to define this formally, then you have two permutations. And in fact, the target can just be the increasing permutation. And you want to find the minimum number of prefix flips that takes you from pi to pi prime. So if pi is 3124 and pi prime is the increasing one, then first you can select prefix of length 3, reverse it, and then you select prefix of length 2, reverse it, and you get the increasing permutation. And this has been studied by people doing genome rearrangements because they like these types of operations. And they were interested in the sort of the worst case, and things are known like every permutation can be sorted in linear number of prefix flips, and the particle constant is still like an open question that people study. Actually, one of the bounds is the only academic paper of Bill Gates. It's also an interesting fun fact about this. But only very recently, in 2015, these three authors showed that it is actually NP-complete to decide if I give you the permutation and I give you the number of prefix flips, whether it's actually possible to sort it or not. And so this is the problem that we will be reducing to the multi-agent path finding. Sounds a bit surprising, right? But okay, let me give you the basic idea. So, and we'll use this 3124 idea. Okay, so if I take a tree that looks like this, then I can, by moving the agents, I can simulate a prefix flip by essentially taking these first three, routing them up, then routing them to the left, and then putting them back to right. this exactly performed a prefix slip, right? But then, you know, in each step, I want to flip a different length of prefix, so I can just do it like this, because then the make span, of course, depends on somehow the sum of lengths. And also you could do all sorts of weird rearrangements around the central vertex that are completely different from prefix flips. So in the ideal world, what we want is that we want to somehow separate it into phases where first we want to forbid these agents to completely use this part. And so they will be forced, some of them will be forced to enter this top part. Then this right path will be cut off, and they can only move on these two paths. And then finally this path will be cut off, and they can move back to the right. And this will be like one round with 3 phases that will repeat exactly k times. So how do we do that? How do we, how do we block certain vertices at given times? Well, there is a black box reduction. It's called blocking path. It's also called blocking path. And so assume that we have some sort of instance which has vertex v, and we want to block this vertex v at time steps 2, 3, and 5. And we're looking for a solution of make span 6. Well, the idea is that we just put a path of length, this is like 11, well, 6 vertices on each side. That goes through V, and we put 3 auxiliary agents here, and 3, which these are their targets. And they are set up in a way that this agent is exactly 6 steps away from its target. This agent is 6 steps away from their target. So the only way to resolve these agents is to let them run through on this path without ever stopping. And if you do so, well, then they block the vertex V at exactly round 2, 3, and 5. But there is a problem with this if you use it as a black box kind of a reduction, I think. The 2 problems for our purposes, but in general, there is one main issue. So if you imagine that these blue agents are very sparsely distributed, that you're actually not blocking the vertex V at most times, then this auxiliary extra path can actually be used by the agents from the main graph to do some sort of rearranging that you don't want to do. It will allow you to do extra things, but this can also be addressed in a black box manner by adding 2 extra paths, like this. This is like the red path, and this is, say, green. And the idea is that on this right path, each gap that was not a blue agent is filled by red agents, and these red agents, they don't cross over to V, but they continue down here. But they guarantee that this vertex is occupied at every point of the schedule. So no agent of the main graph can actually use this vertex. And on the other side, it's kind of symmetric in the sense that these green agents are waiting, and they'll be merging with these blue agents. And again, this vertex that's adjacent to V will be actually blocked at every point of the schedule. So I said these agents kind of walk in a line, and these ones are merging into the blue line. And after 6 steps, you reach the final destination. But both of these neighbors of V were blocked at all times, so no agent can escape. Well, and now, I mean, technically, we could use this to do the reduction from pancake flipping by simply adding this to every possible vertex, which would show that the problem is NP-hard on trees. But we also wanted few leaves. We don't want there to be many leaves. So we do kind of a slightly different thing. Bear with me. This is still the main part of the graph, the one that corresponds to the flips. And then here on the left is exactly the gadget of the blocking path as I described. So it kind of cuts off this path whenever it is needed. Whereas on these 2 parts, we kind of have only this. We only have this right path right part of the blocking gadget, and the blue agent, instead of crossing over, they're kind of like outputted on the main path and letting run to the outwards, because that's good enough at that point. Like you have to guarantee that no agents, none of these like colored agents can actually stay on here during the sort of sorting rounds. So these auxiliary agents will push them outwards if they ever stay there, and they have no chance of getting back. And then the sorting step is exactly as I kind of described at the beginning. Several agents move there, move back, and then move back. And this is repeated for k rounds. And there is a solution to this if and only if the original permutation can be sorted within k prefix flips. Let me actually show you. We've done a sort of a demonstration for AAAI, where you can say that you want this particular permutation, 3124, with 2 flips. It generates you the instance. You know, the bold ones are the main ones, and then these other agents are the auxiliary one. So if I don't do any flips to the input permutation, then these auxiliary agents, they first like allow these main agents to move to the top part, but then they cut off the input, and this top part can now move here. And now the top part gets cut off, and they can move back. And this top part now it's kind of pushed away by these agents, so it cannot be used again. And then second round starts with the same thing. The agents can move up, then they're allowed to transfer to the left, and then they cut off, and they can rearrange back. And that's the whole introduction. And if you know, if in this particular case you want to do prefix flips of length 3 and then 2, which was the solution, then this is how it looks. Right, so these 3, 1, 2 gets put to the top, then it returns here, then it goes back. Now it waits until the start of the next round, and then the first 2 go there, move back, and finally they wait until this is opened and they return back. And this particular tree has, if you count it, exactly 11 leaves. So it's like at the end of these paths. Okay, and this is a link to this if you want to play around with this demo. And so just to conclude, well, the main takeaway should be that it's really hard, that the multi-agent path finding is hard on trees with just constantly many leaves and constant number of internal vertices, not at the same time. But so for the future, what we can do is explore if this kind of very restricted hardness of multi-agent path finding can be used to deduce hardnesses of some other problems within similarly restricted domains. And also if we can combine the structural parameters with some other restrictions like the number of agents or make span, since the structure alone doesn't seem to help too much. And that's it. Thank you.
Any questions?
Or maybe you said it, but you said you forbid crossing over
Swaps, yeah.
swaps. So does any of this part of the doc changes when you? I mean, what's the standard? Because you were saying these people prove that, these people prove that, and we forbid that. So is it that they are using your notion, or?
So I think both of them are studied, both swaps and null swaps. I feel like more people study swaps, but I wouldn't put my hand in the fire. I think it's pretty even. So in particular for our results here, the distance to clique one gets easier because the swaps are really what's causing a lot of these issues, because if you don't have swaps, you can kind of do everything within the clique, and you're done with lots of these arguments easier. For the hardnesses, for these 2 hardnesses, we actually do not know if they work without swaps. So the one for this pancake sorting, I think I had at some point a rather complicated idea how one could go around this, but I wouldn't put it's never written down, but I think that this might go through. The one for the vertex cover, that one is like really kind of somehow crucially depending on the swaps. There it's like not obvious at all how one could do. So there is still possibility that on vertex cover, when the swaps are actually allowed, then there might be an efficient algorithm.
So, like as far as I remember, a picture of the structural parameterizations that you consider. There was one that is still possible to have an efficient algorithm, which was something like clique cover.
Yeah, so the clique cover is not it's not like nothing is published about that. So I believe this is a there's like an edge clique cover and vertex clique cover, right? There are two of these variants. Not sure which one is supposed to be the default one, but you can actually get hardness for vertex clique cover in a fairly simple way, because you can somehow kind of distribute all the hard parts to an edge of a graph that's several partites, which each part is a clique, but the agents are forced to go within the clique. So you have the fact that you have few cliques is like not helpful for the agent because they have to run through them. So it is NP hard for this vertex clique cover number, and for the edge clique cover number, it's actually like one last bit of hope that the distance to clique algorithm might actually extend to that case, because in some sense it's pretty similar, just slightly more complicated setting, right? Yeah. All right. You had a question also?
Yes. So for max leaf number, the number of agents is quite large, right?
Yes.
So, you know, any intuition if also the number of robots is small.
Oh, right. You mean like add the number of agents as a parameter?
Yes.
So this is a particularly hard problem on trees in general. It's very much open to whether it's FPT by number of agents on trees.
Okay.
However, on trees with few leaves, I don't believe. Like, I think it's not something that is written anywhere, probably, but I think that we believe that on trees of this kind, where there are few leaves and there are few agents, then it should be actually solvable efficiently. I believe on like max leaf number in general, not only on trees, like that max leaf number plus number of agents is a strong enough parameterization. But like I said, it's actually open, and I think many people are interested in the setting of K agents on general trees, and that one is wide open.
Any other questions, comments, criticism?
Contradictions.